Hello everyone. In this video we will discuss about singular value decomposition and its applications. In linear algebra we have a number of factorizations like LU decomposition, QR factorization, eigenvalue decomposition, and we also have singular value decomposition. Singular value decomposition is one of the very famous decomposition because it has a number of applications in the domain of science and engineering and many other fields, and we will be seeing some of the very important applications in this video. So let's start with the definition of the singular value decomposition. SVD is a decomposition for any generalized rectangular matrix, unlike eigenvalue decomposition, which is confined to square matrices and only if the matrices are diagonalizable, whereas SVD is very general in the sense that any matrix can be decomposed into U sigma V transpose. As we can see here, A is a rectangular matrix M cross N, and U and V are square matrices, and the sigma, which contains the singular values, is a rectangular matrix. Rectangular diagonal matrix, we will see how the matrix would look like. So where U contains eigenvectors of A transpose and V contains eigenvectors of A transpose A. So sigma contains it's a rectangular diagonal matrix with R non-zero square roots of eigenvalues of A transpose A or A transpose. Important thing to note, the eigenvalues when we compute, they would be similar for A transpose A and A transpose, and we take the square root of it, and those will be the singular values. Those singular values will be there in the diagonals. So here where R stands for rank of a matrix. So let's see how the matrices will look like in terms of dimensions. So for example, if you take a fat matrix for A, you will have U sigma V transpose as follows, and important thing to note is the sigma, which is a rectangular diagonal matrix where all the diagonal elements contains singular values and the rest of the values are all zeros. And when you take the tall matrix, our decomposition would look something as follows, where sigma would be once again a tall matrix where we have a number of zero rows once we have placed all the singular values in the diagonal position. Let us see some more details about the dimensions of matrix involved in SVD computation. So these are the two cases we have seen, M less than n and M greater than n. But if you observe carefully, the sigma matrix has a lot of zero columns, and this gets multiplied with the rows of V transpose, which does not result in any non-zero value. So we can exclude these zero column vectors and also the row vectors in V transpose so that computation and representation becomes simple. The same thing goes here. In the sigma matrix, there are number of rows which are filled with zeros, and whatever may be the U values, they get multiplied with these zeros, so there is no use of utilizing this U column vector. So the alternative representation, simplified representation, would something like this. So we have eliminated all these column vectors of sigma and also row vectors of V transpose, and we got the alternative dimensions as M cross M for sigma and M cross N for V transpose. So in the same way, we have for the other case, M greater than n, we will have representation something like this. Here we eliminated the columns of U and also some of the rows of sigma, and our sigma matrix this SVD got a simplified representation. So this, when we implement in Python, we have a function called as SVD in linalg library. There we have control over these versions to use based upon this variable called full underscore matrices. If you set to false, we will be utilizing the simplified representation, and if you set to true, we will be utilizing the full representation of SVD. But the result wise, they result in the same. It's just that the alternative latter representation has a simplified computation as compared to the earlier one. Let us see now one of the important property of SVD related to orthogonality. This is the SVD representation. A is equal to U sigma V transpose, and we know U is constructed by using the eigenvectors of A transpose and V using eigenvectors of A transpose A. Both A transpose and A transpose A are symmetric matrices, and we can choose orthogonal eigenvectors for both these matrices. So U and V are actually orthogonal matrix which contains orthonormal eigenvectors. So since they are orthogonal, we have these beautiful properties where when we multiply any two orthogonal vectors, you get 0, and when you multiply with the same vector you get non-zero. So these properties will help us to actually compute V from U and U from V. So usually what we do is we compute first the smaller dimension matrix U, and later we compute the V matrix by utilizing this orthogonality property. So we multiply, suppose if we multiply U1 on both the sides of A and this whole sequence, everything else will become 0 except this particular first term, and this property will be helpful to find out the other matrix V when you have U. So we use this very frequently while computing singular vectors. So this is the matrix representation. U transpose equal to U transpose U is equal to I, and the same thing for V transpose equal to V transpose V is equal to I. So the important thing to note is this is also applicable for complex matrices. We are working with the real matrices, but for when it is complex, we can replace this transpose with Hermitian. So these are the applications of some of the applications of singular value decomposition. There are many other applications which I have not listed, but the important ones which are mainly used in the domain of engineering is what I have listed here. So in linear algebra, we use SVD for computing the inverse for any matrix. We know how to calculate the matrix inverse when the matrices are full rank. But when the matrices are not full rank, how do you compute the inverses? And that is discussed. The SVD helps to do that. So we use SVD to find the inverse for any matrices, or you can say pseudo inverse for any matrix. And one of the applications of SVD is also to have a low rank representation of any matrix. We will see one theorem where it states that SVD is the matrix. SVD is the best method to find out the low rank decomposition or low rank representation of any matrix. And we have a number of applications in image compression, and in computer vision we can do face recognition using eigenfaces, and in recommender systems we can use for matrix factorization, for decomposing user item matrix. And the main other important application, especially in the domain of data science and machine learning, is dimensionality reduction, where we use principal component analysis, where high dimensional data is represented in low dimensions by eliminating the unnecessary dimensions which has redundant or noisy information. So let us, before we actually see these applications, let us see how we can compute SVD by taking few examples. So let's take this rectangular matrix. We know A is U sigma V transpose, and if we represent in the form of vectors, we have something as follows, where sigma 1 is the first singular value, U1 and V1 are the vectors corresponding to U and V, and K is the value which lies between which is less than or equal to a minimum of n comma m. In terms of when we represent full SVD, we will have it is K is equal to minimum of n comma m. So let's compute each of those values. So let's start with A transpose. Our goal is to find the U and V. So we know that U is the eigenvector matrix of A transpose. So this is A transpose. We compute the eigenvalues, which are 3 and 1. take the square roots, we'll get singular values as sigma 1 equal to root 3 and sigma 2 is equal to 1. So when we represent in the form of a diagonal rectangular diagonal matrix, this is how sigma will look like. So and if you compute the eigenvectors, we get u1 and u2, and finally we get this U matrix. In the same way, we will find V matrix, but instead of computing the eigenvectors of A transpose A, there is an easier way to get it. We know A is U sigma V transpose, so we can send the individual singular values to the other side and compute this. Because all these eigenvectors are orthogonal, so when you multiply u1 with both left and right side, all other terms will become 0 except this term. So in this way we can nicely send these vectors to the other side and compute the vi values. So v1 is as follows, v2, v3 as follows, so we get the final V matrix. So in this way we compute singular values for any rectangular matrix. So let us take one tall matrix example. Here A transpose A is as follows. Lambda 1 and lambda 2 are 15 and 0. As you can see, there is a 0 eigenvalue, so the singular value corresponding to that is also 0. As you can see here, this is a rank 1 matrix, it's not full rank. So sigma 1 is root of lambda 1, which would be root of 15. So finally this is the sigma matrix, when you compute the corresponding eigenvectors, this is what we get, the V matrix. And once again, since V is also a eigenvector matrix and they are all orthogonal, so we can utilize the orthogonality property and compute the U values. So when you multiply V on both sides, all other terms will become 0, only one term will remain, and you can send the sigma to the other side and compute the u1 values, u1, u2 and so on. So this is the final matrix we get for U. So these are two examples. We can decompose any matrix into U sigma V transpose. Now let us see one of the application in maths. In maths we know how to compute inverse, especially when the matrix is a square full rank matrix. We know how to compute it. So if you want to solve a system of equations, and this inverse will help us a lot. If you have Ax equal to b, x equal to A inverse b, and this is good when the matrix is square and also full rank, so you get a perfect unique solution. But when the matrix is tall matrix, where you have dependent columns and dependent rows, and assume that it is a full rank matrix, so it forms a full rank overdetermined system of equations, and assume it is not in the span of A, then there is no solution, and the only solution which we can get is to project onto the space of A, and we can obtain this least square solution, x is equal to A transpose A whole inverse A transpose B. So this is when the matrix is full rank and when there is no solution. So let us take the case of m less than n, where we have fat matrix, and usually we have dependent vectors, and we get infinite solutions. So whenever we have infinite solution, the best solution which we could take is the solution with the least norm, and that minimum norm solution can be obtained by this matrix. So these expressions have been proved in another video in this channel. So, and finally the important one is irrespective of dimensions, whether it is m equal to n, m less than n, or m greater than n, you take any matrix with any rank and it can be fallen to any case. We can use SVD to find out the pseudo inverse, and the pseudo inverse gives us the minimum norm least square solution. So that's the greatness of SVD. It can be used for, it's a more generalized for any matrix. There is no condition on the rank or anything. These are also pseudo inverses. They also don't have perfect solution, but they are good in some sense. One is good in the least square sense, least square error, and the other gives us a solution which has a minimum norm. I mean, like here we have infinite solutions, so we are interested in a solution which is good in some sense, and that sense is having a minimum norm. So whereas in SVD we get minimum norm least square solution, and this works for any matrix. So this is the first application in linear algebra where you can find the pseudo inverse using SVD. Let us see the expression. So this is what I was saying: Ax equal to B, and A, if you represent in the form of U sigma V transpose, you can multiply the corresponding transpose on both sides, and you will easily obtain this A star or pseudo inverse as V sigma plus U transpose. Here the sigma plus for a tall matrix would look like this, the inverse of singular values, and for a fat matrix it would look like this. So in this way, any system of linear equations, irrespective of their rank, can be solved using singular value decomposition. So let us see one example of how we compute pseudo inverse for a fat matrix using SVD. So when you compute U sigma V transpose for this example, we have something as follows, and pseudo inverse can be computed by A plus is equal to V sigma plus U transpose. So this is the V, we are directly using it, and sigma plus is the inverse of the singular value. So we have the singular value as root 3, so the inverse of singular value is 1 by root 3 and 1, and we have the U matrix which is shown here. So when you multiply it, we get something like this. The important thing is this inverse which you computed using SVD matches with the SVD, matches with the inverse computed using minimum norm solution. So when we have a fat matrix, we have seen just now that we can use A transpose inverse. So this gives us minimum norm solution. So in this way, when you compute A transpose and multiply with A transpose, you get the same solution. So minimum norm solution and SVD results in similar. It's just that SVD based inverse is applicable for all the matrices, whether it is fat, tall or square matrices, whether it is full rank or not a full rank matrices. We are using here NumPy library. This is the input matrix A, which is of dimension 2 cross 3. We are invoking the linalg and SVD function, which is part of linalg library, to compute the U sigma and V transpose, and we reconstruct this using here. So if you observe the output, this is the input matrix A, U matrix is this, singular values of or 1.73 and 1, and V transpose is this. Note that there is no third row in V transpose because we have third column in singular value matrix as zeros, so there is no use of putting this. You can control that by changing from false to true and appropriately adjusting the code. So the reconstructed matrix, if you see, it is exactly similar as the original matrix because we have used all the singular values. Let us see how pseudo inverse can be computed using SVD. First, we initialize a variable sigma plus, and we obtain the values by taking the inverse of each singular value, and later we reconstruct pseudo inverse by using VT transpose sigma plus U transpose. So if you try to print all these values and use this verification, so this was our original matrix A. After computing pseudo inverse, we got this. To verify it, we are multiplying A plus and A. So both these should give identity, and when we multiply with A, we should get back our A matrix here. And also when you do A plus into A plus, we are getting back our A plus matrix. So in this way, we compute pseudo inverse by taking the inverse of each singular values and multiply with its VT transpose and U transpose. One of the other use case of singular value decomposition is to obtain a low rank representation of any matrix. We know SVD is A is equal to U sigma V transpose, and we can obtain AK, which is the kth rank approximation of the matrix A, by using SVD. One of the theorem states that SVD gives the best kth rank matrix as compared to any other kth rank matrix, in the sense that it will have the least Frobenius norm, which is stated using this theorem called as Eckart-Young theorem, which states that the best low rank approximation AK of a given matrix A is found by truncating its SVD to its first k largest singular values and their corresponding singular vectors. So the best in the sentence mean that the error between the A and AK computed using Frobenius norm is less than any other matrix BK. So if you take the kth rank approximation of all matrices and if you compute the error with the A matrix, the matrix which is obtained using SVD, which is AK, will have the least error as compared to any other matrix. That's what this theorem states, and in that sense, SVD gives the best kth rank approximation of any matrix. So this low rank approximation can be obtained using SVD as follows. So as we stated, we will, rather than taking all the singular values, we will be taking the first k largest singular values and its corresponding singular vectors, and we construct U and V matrix and thereby construct AK vector. So we are not using all the eigenvectors. We are just using the k largest singular values and its singular vectors to obtain the rank k approximation of a matrix. So let us now see one example for computing the rank k approximation of any matrix. Let's take this matrix A, which is of rank 2, and the singular values are root 3 and 1, and if you compute the singular vectors for the largest singular value, which is root 3, we get U1 and V1 as follows. And this V1, as we stated earlier, which is obtained by using the orthogonality property of eigenvectors. And once we obtain the largest singular value, we can get the best rank 1 approximation of this matrix by constructing U sigma V transpose, but using only one singular value and one singular vector. So when you compute this is what we get it. This is the rank 1. As you can clearly see, there is only one independent column vector, and this is the rank 1 approximation of the matrix A. So this is the final answer. Our original matrix was rank 2, and we obtained the best rank 1 approximation of the matrix A. So in this way we can obtain for any matrix. We'll take one more example. So here we have matrix A with rank 2, and this is what we found out just now. This is the rank 1 approximation of the matrix A. Let's take another example with the dimension is 3 cross 4, which is of rank 3. So there are 3 independent vectors. This fourth one is a dependent vector. So we have 3 singular values, non-zero singular values, and if you see the best rank 2 approximation of this matrix and rank 1 approximation of this matrix, it will be as follows. This is the rank 1 approximation of the matrix computed using SVD by taking only the largest singular value, which is sigma 1 equal to 2, and keeping all other singular values as 0. Best rank 2 approximation of a matrix can be obtained by retaining the 2 largest singular values, which is sigma 1 equal to 2 and sigma 2 is equal to root 2. As you can see here, A2 is the best rank 2 approximation of the matrix A. So in this way we can obtain the kth rank approximation of any matrix of any dimension by using SVD. Let us see one application in the domain of image processing where we can use this idea to compress any image. So A has been expressed using singular value decomposition, and where here we want to use this image, which is a real image, and we want to convert into grayscale and apply SVD and retain only few singular values and see how the representation and the output would be, and how it will be helpful for us in image compression. So let's I'll show this demo. As you can see here, we have 4 singular values. Now a lot of blurriness, 8 singular values. This is the output, and when you take 16 singular values, as you can see, almost the details are visible. 32 singular values, we have this kind of a image with 64, and 128 singular values. We will have almost near to the clarity without losing much of the details. 256 singular values, 512 singular values, and we are hardly seeing any differences towards the end when we are introducing lower and lower singular values. So in this way we can use SVD low rank approximation for image compression. Let us now see how we can implement the rank approximation of a matrix using SVD in Python. We are using here NumPy library. This is the input matrix A, which is of dimension 2 cross 3. We are invoking the linalg and SVD function, which is part of linalg library, to compute the U, sigma, and V transpose. And we reconstruct this using here. So if you observe the output, this is the input matrix A, U matrix is this, singular values of are 1.73 and 1, and V transpose is this. Note that there is no third row in V transpose because we have third column in singular value matrix as zeros, so there is no use of putting this. You can control that by changing from false to true and appropriately adjusting the code. So the reconstructed matrix, if you see, it is exactly similar as the original matrix because we have used all the singular values. Now let us see how we can represent rank approximation of a matrix using SVD. So as we have computed U sigma V transpose, we can take k is equal to 1 and obtain the rank 1 approximation of the original matrix. So when you take only one singular vector and one singular values, you will be getting U1, UK, SK and V transpose. So we will be using this one singular vector and one singular values to reconstruct the matrix AK, and this is how it looks like. As you can see here, this matrix has only one independent vector and the rank is 1. So we got the best rank 1 approximation of the original matrix using SVD, and we can implement in Python as given here. Let us now discuss how SVD can be used for image compression by using the low rank representation. So here we have written code in Python. So this is, we are loading the NumPy and Matplot libraries here. We are also using SK image library. First we try to read the image. So we have used a image which is loaded already here. And we computed all the three components, RGB components, and we apply SVD for each of these components through this method. And once we obtain SVD for each of these components, we try to reconstruct for with just 100 singular values and see how the output image would look like. So we have plotted both the original image and the rank approximation. So if you take a 100 rank 100, this is how it looks like. So let us change these to another value, say rank 10, and see what sort of reconstruction it gives. As you can see here, it was very blurry. A lot of components are missing, but this is a more compressed version because we are only using the 10 singular values. When we use for example 50 singular values, we get result something like this. It is almost clear. It is but slightly lesser compression as compared to rank 10 singular values. And then if you try to represent, say, using 500 singular values, it would look exactly similar to this. So in this way, by actually modifying the k, we can appropriately choose control the number of singular values and thereby reconstruct the image of arbitrary compression levels with little at the cost of little degradation in the quality. So this is how image compression using SVD can be done by using a low rank representation. In this video we will discuss about dimensionality reduction. We'll first discuss about various methods which are available for dimensionality reduction, and later we will particularly focus on PCA based dimensionality reduction. We'll see PCA, which is principal component analysis, using both covariance method and also using singular value decomposition. Finally, we will see the implementation of PCA using SVD, which is the computationally efficient way of doing the PCA. Dimensionality reduction is the process of reducing number of input variables or features. which means to remove the unnecessary, redundant, or noisy features which are irrelevant in a dataset by preserving as much relevant information or structure as possible. So let us see how it can be done and what are the methods which are involved. So broadly, it can be categorized into two categories. One is feature selection based and feature extraction based. In feature selection based, these methods do not change the feature values. They exactly retain as it is, except that they select relevant features. Whatever are the existing ones, they select from the set rather than modifying the features. Whereas feature extraction based depends or modify the features so that it transforms into a more relevant features and thereby avoid the unnecessary redundant information. There are three different categories in feature extraction. One is linear methods, the other category is non-linear methods, and the third category is neural network based methods. In linear methods, we have principal component analysis, PCA, singular value decomposition, SVD, linear discriminative analysis, independent component analysis, factor analysis, etc. In non-linear methods, we have kernel PCA, TSNE, and so on. In neural network based, we have famous autoencoders, variational autoencoders, and deep autoencoders. In this video, we will be particularly focusing on PCA based dimensionality reduction. We will also see how SVD is very much close to PCA and how PCA can be implemented using SVD. Let us now discuss about principal component analysis. As we have discussed earlier, it is a linear dimensionality reduction technique where it transforms dataset into a new coordinate system where the axis of this coordinate system comes from the greatest variance. So the first greatest variance gives the first major axis and the second greatest variance gives the second axis. So we would like to transform each of these dataset into that particular coordinate system. We can view PCA as that, and the second definition we can see as to transform a set of correlated variables into a completely uncorrelated variables called as principal components. So many, as we have seen earlier, a lot of features are correlated, can be correlated, and we would like to reduce those redundancy by moving from correlated variables to the uncorrelated variables. So these are two different views. Let us see more mathematically and understand how PCA is computed. Let us see how principal component analysis can be computed. Let's start with this data set. We have a number of points here. Our job is to find out these axes along which there is maximum variance and also second maximum variance. So since it's a 2D image, we are showing it as an ellipse, but if you go into higher dimensions, we'll have other axes also. So let's see how we can compute these axes along which there is maximum variance. Let's consider a dataset X represented in the form of a matrix of dimension n cross d, where n represents number of samples and d represents number of features. Our first step is to mean center the data. We compute the mean along all the samples and subtract that from each of those so that it becomes mean centered. And we compute the covariance matrix also. So let's see how we can compute these axes. First, let's formulate this as an optimization problem. So if you see this, our job is to find out this W vector along which we are trying to project, and our goal is to actually maximize this variance. Once after projecting each of these data points onto this axis, we would like to see along which is that axis which gives the maximum variance subject to the condition that weight vector is equal to 1. And this we do it because since we are maximizing it, it can go until infinite. So to have a constraint, we are using this. But our job is to how do we maximize the variance of the and what should be the axis W such that the projection of each of these data points onto this axis will result into a maximum variance. So that is the axis which we are interested in, And this problem can be formulated something like this. We are just representing xc transpose xc as c here, and this can be solved using Lagrange multipliers as follows. So this constraint has been brought into the main objective function, and when you apply gradient and when you solve it, we get an equation something as follows: cw is equal to lambda w. This is what eigenvalue definition or eigenvectors definition. Ax is equal to lambda x. So we are essentially trying to find out the eigenvectors of this matrix C, and those are the vectors which are going to give us the maximum variance for this projected data. So towards that, we find out the eigenvectors of this matrix C, and thereby obtain the all these axes along which there is maximum variance. The matrix C here is a symmetric matrix, and we can choose orthogonal eigenvectors to this matrix C. And so the W vector would be an orthogonal eigenvectors, and those form these axes of this ellipse or in higher dimensions. So let us now understand some geometric meaning of what is happening here. So we have a set of data points, those have been spread along certain directions, and mathematically we came to understand that if you are able to find out the eigenvector of a maximum eigenvalue, that vector is going to give the spread of the data along a particular direction. And why is it happening? It is because when you project each of these data point onto this vector w, that's what we are doing here. When we multiply xc with w, each sample, each row in xc is a sample, and when we are multiplying that particular row with w, we are multiplying each sample with this w vector. So which means to do a dot product between each sample and w vector, and this dot product would be maximum when the angle subtended between them is less. So when the data is along the w vector, we will have this maximum value. So we are therefore our eigenvector here is giving you that direction along which when you project the data, you will get the maximum variance. So in the same way, for the second eigenvector will give the second maximum variance, and so on. Let us summarize what we have discussed in principal component analysis. We considered an input data in the form of a matrix of dimension n cross d, where n is the number of samples and d is the number of features. We centered the data, and we later computed the covariance matrix, and we have performed eigenvalue decomposition to the covariance matrix, where the q indicates eigenvector matrix, where lambda indicates the diagonal matrix with eigenvalues as the diagonal elements. And out of these eigenvalues, we have chosen the k maximum eigenvalues and its corresponding eigenvectors and constructed the matrix qk. And we eliminated all of the other components. This is how we do dimensionality reduction, where we remove the unnecessary redundant directions, and we focus only on the more relevant components. So this is how we project, where we multiply with the qk matrix, and as qk matrix is orthogonal matrix, so when you multiply with its qk transpose on both the sides, you can get back this centered matrix, and if you add mu, you can get back the original matrix X. So in this way, this was the summary of what we have done in principal component analysis. Let us now discuss two different ways of computing PCA. One is the covariance based computation of PCA, and the second is SVD based PCA. In both the methods, we'll start with our input matrix X, we center them, and later we compute covariance matrix in the case of covariance based PCA, and whereas in SVD we don't do that. In the later step, we compute the eigenvalue decomposition for the covariance matrix C, and whereas in SVD based method we do singular value decomposition for the matrix XC. If you observe, Q matrix is nothing but the eigenvectors of the covariance matrix C, which is XC transpose XC. In the same way, in V is also, we know that V is constructed by computing the eigenvectors of XC transpose XC. So in a way, both are doing the similar things, where we are utilizing the eigenvectors of the matrix XC transpose XC. So we get principal directions in the matrix Q and V, and variance values, or the how much is the variance in the data, is quantified using eigenvalues in the case of PCA based method, whereas in singular value based PCA, our singular values quantify the amount of variance. In fact, lambda and singular values are very much related. You can compute singular values by taking the square root of the lambda values. So out of the many principal components, we take the k dominant PCs by choosing the eigenvectors of the k maximum eigenvalues. So those eigenvectors are placed in Qk and Vk in the case of SVD based PCA, and projections are calculated as follows, where z is equal to xcqk, whereas here z is equal to xcvk. So later we can do the reconstruction, as Qk is orthogonal matrix, and we can re-add the mu term to get back the non-centered data. So PCA is almost always implemented via SVD because there is a computational advantage as compared to covariance based method. And also PCA eigenvectors are nothing but the SVD right singular vectors. Just now we have seen the right singular vectors and the PCA eigenvectors are similar, and PCA eigenvalues is equal to the squared singular values. So this is how PCA based covariance based method and SVD based PCA are related. Let us summarize the steps of dimensionality reduction using SVD based PCA, and we'll solve one problem. So as you can see here, X is our matrix, and when you center we get XC. We apply SVD to compute U sigma V transpose. We take the top k singular values and its corresponding singular vectors, which we obtain from Vk, and we project that data and we obtain the matrix Z. This is how we get the dimensionality reduced data set. So let us see one example to solve it. Consider the matrix X with 3 samples and 2 features, and as you can see they are very highly correlated, and when you do mean centering, this is what we get it. And when you apply singular value decomposition, you get U sigma V transpose. But as you can see, there are only one singular value, the other singular value is 0. So we can eliminate this redundant data, and we can only consider the singular vector of the maximum singular value, which is from the V. And when you do that, we have something as follows. So we consider only one singular vector V1 and constructed the Z matrix, and when you try to reconstruct, we get X approx similar to our centered data, and when you add the mean, you get back to the original matrix X. Let us now discuss how PCA is implemented using SVD in Python. We are utilizing the libraries NumPy and matplotlib. So first we created an sample NP array with 5 samples and 2 features as a 5x2 matrix, and we printed it here. We computed the mean centering along axis 0 across all samples. We got the matrix XC. And then we apply the singular value decomposition for the matrix XC. So as we have just now seen that we can use SVD also to compute the PCA. We are invoking this method SVD, which is part of linalg, and this library is part of NumPy library. So we compute U sigma V transpose for this matrix XC, and once we obtain these singular values, we utilize the V matrix, which contains the principal directions, and later we take only since we have 2 columns, there is scope for 2 principal components, but we have eliminated the redundant one, and we have only chosen the one which has the maximum covariance value, maximum singular value. As you can see here, the 2 singular values 2.635 and 0.46. So we are eliminating the eigenvector, eliminating the vector corresponding to this singular value, and we are utilizing only the vector corresponding to 2.63. So that's what is being done here. We are taking only the first singular vector of the first maximum singular value, and later projecting this data to construct the matrix Z, and later we use it once again to reconstruct back the data. So by just using the one principal component, we are able to reconstruct the original data. Let us see what sort of error it has as compared to the ground truth. So 2.36 and 2.54. So our original data was 2.5 and 2.4. So it is almost close. So in this way, wherever we have redundant data, we can eliminate by appropriately choosing the dominant principal component and reconstructing the matrix. So this is how PCA is implemented in Python. Let us see one of the application of PCA called Eigenfaces. Eigenfaces can be used for face recognition. So let us see how it works. So eigenfaces are a set of basis faces that capture the most important variation among a collection of face images. It is actually a low dimensional representation of the face images which capture the essential information and eliminates unnecessary information. So let us get the intuition by taking a small example. So let's consider 1000 face images which are grayscale and of size 100 cross 100, and all these images, we make sure that eyes and nose are aligned, and each image can then be represented as a 10,000 cross 1 vector which is high, and there is a lot of redundant information. So we can use PCA to represent in a low dimension, and this low dimensional representation of each face is called as eigenfaces. So we use this representation to do face recognition. So let us see it. So let's consider, we know already the steps involved in computation of PCA, which is to compute the mean, center around the mean, and compute the covariance matrix, and compute the eigenvectors which corresponds to the eigenfaces. So here, so all these images which are listed here are the eigenfaces. So this is the mean face and this is the eigenface. So when I say eigenface, this is the low dimensional representation of the original face, and in practice we compute these by computing the V matrix in SVD, and once we obtain the low dimensional representation of eigenfaces, we can represent any face in terms of this eigenface, and we can obtain the weight vector corresponding to every face, and these weight vectors can be later used for face recognition. So suppose if you represent a image in terms of eigenfaces, and if you reconstruct, it would look something like this. Depending upon how many eigenfaces you have used, it shows the amount of clarity in the images. So let us see how this works for face recognition. So in face recognition, when you get a new test face, we try to compute the weight vector by representing in eigenfaces, and we compare this weight vector with the already stored weight vectors, and thereby recognize the test face with the existing set of images. So this is how eigenfaces work for face recognition. That's how eigenfaces can be implemented. Here we are using various libraries to implement this. So we are using OpenCV, NumPy, Matplotlib. So we have all the face images here in the faces directory. We are reading each of those faces using the OS library and using OpenCV, and we are computing the mean and centering each image to its mean, and we are applying SVD to compute the PCA. As we know, PCA can be efficiently implemented using SVD, so we are invoking the SVD function as part of linalg library, which is part of NumPy, and computing U, sigma, and V transpose. So an important thing to note is our eigenfaces are nothing but this V transpose. So each row is an eigenface here. So we are trying to display here 6 eigenfaces through this matplotlib, through this function, through this loop, and later we are setting k is equal to 20, which means we are trying to reconstruct using 20 eigenfaces, and reconstruct all the eigenfaces multiplied by weight to obtain the reconstructed image. So later we can also use these weights for recognizing any image, where you send a test face, compute the weight vectors, and compare it with all the weight vectors of the images which are there in the database, and recognize the appropriate image. The output, I'll run it once again. So this is the mean face, So these are the eigenfaces. So 6 eigenfaces has been displayed here, but we have computed 20 eigenfaces. So this is the reconstructed using 20 eigenfaces. So let us change this eigenfaces number and see how the reconstruction error changes. Suppose let's take 100 eigenfaces and run this. So if you run this is the mean phase, and eigenfaces, I am displaying only 6 eigenfaces here, although we computed 100, and this is the reconstructed eigenphase. As you can see, the phase is much more proper. So we have increased the number of eigenfaces and its corresponding weights. So the summary is we can use these eigenfaces to represent any phase image, and also we can use this weight vector for phase recognition. So if you have any test image, you compute the weight vector by representing in eigenfaces, and compare this weight vector with all the already stored image weight vectors, thereby recognize the phases. So this is how PCA can be used for phase recognition in eigenfaces, using eigenfaces.